Hi, my name is Matt Callaway, and my research project for the STAR Showcase is on classifying interstellar objects based on features of their density maps. This summer, I was mentored by Professor Gordon Richards and Weizhang Yu, who are both in the physics department. So to start off, data for these observations comes from sky surveys, which are a medium for gathering astronomical data from a bunch of telescopes. The purpose of this project is to increase the efficiency of interpreting these sky surveys, and the three main objects being observed and interpreted are stars, galaxies, and quasars. Now, what I mean by observed is these are the objects that this project is aiming to get us closer to identifying. Currently, objects in the sky surveys have to be searched for and identified by humans, which isn't very efficient. A much better method is to develop an AI that can identify objects itself. I mentioned that one of the objects being observed is quasars, but what is a quasar? Active black holes or black holes that are consuming mass that are at the center of massive galaxies are called active galactic nuclei. And the most luminous of these are called quasars. So to classify these objects with an AI, we need a simple way to present the readings of these objects, and that simple way is through a density map. These pictures on the left side are examples of light curves, which are generated based on the data of a random quasar, star, and galaxy. And these light curves can then be used to create density maps, which are what's photographed on the right here. The three density maps here are of different band types, G, R, and I, and each one of these bands encompasses its own range of wavelengths. And all these are actually density maps of the same galaxy, but they appear different because each map is using a different range of wavelengths to create it. The last major parameter used when creating these density maps is bin size, which determines how much area is being read and how much is being displayed. This is really important because reading too much data means you won't have as detailed of a graph because you have to fit more into the same size image. But if you don't make the bin size large enough, or which means you don't include enough in the map, the image becomes empty and you might not have enough information in it to actually identify, is it a star, is it a quasar, or is it a galaxy? So the conclusions of this are that the machine learning is the best and most efficient and accurate way to go about developing an effective algorithm for identifying objects from their density maps. This involves identifying large amounts of data and feeding these answers to the algorithm, so it eventually develops an understanding of what a quasar looks like, what a star looks like, and what a galaxy looks like when presented under specific parameters. The bin sizing will fall into the range described earlier, where it's in that sweet spot where it's not too much data and also not enough. The band types will be used in combination, and all parameters will be consistent in their use to avoid discrepancies in training the algorithm. Future work on this project will likely be further optimizing the parameters to generate these density maps, which would include finding an exact bin size to use, prioritizing parameters based on their accuracy, and using data from other sky surveys to further develop the identification algorithm. This concludes my presentation. Thank you all for watching, and I hope this has been informative for you.